We'll kick us off then. Hello, everybody, and welcome to the last in our series of webinars on our recent report called the Solid-State Lighting Review of Health Effects that was published in October last month. My name is Michael Scholand, and I work for the IEA 4E Smart Sustainability in Lighting and Controls, SSLC Platform, and we are a technology collaboration program organized under the IEA, but independent from it. And I'm joined today by the lead author, in fact, of the health report, Christophe Martensens from CTSB in France. Now, I'll just read a brief bio from him in a second. I just want to do a couple housekeeping points. You'll see at the bottom of the screen in Zoom, you have the option there to, there's a Q&A box to post questions. And so I'd invite you at any point during the presentation today to post questions as we go along. We will wait until the end, and then we'll read those questions out loud, and Christophe will respond to them. Or alternatively, if you like, when we're in the Q&A session at the end, you can also click the button that says raise hand, and then I will recognize you, unmute your line, and then you'll be able to ask your question live to Christophe. So it might be easier in some cases if you need to describe a scenario to simply ask it that way as opposed to typing a long question. So it's up to you. Q&A at any point is fine during the call. It won't disturb Christophe's slides, and then raising hands at the end. So without further ado, let me read Chris's bio so you have the background for his experience. Christophe Martensens is a physicist working in the field of optics and lighting at the CSTB in Grenoble, France. He works for governments, public agencies, and municipalities to improve the quality of lighting installations through a careful consideration of environmental impacts and human health effects. He is the current president of CIE France and a recipient of the 2024 Fresnel Medal awarded by the French Lighting Association. So Christophe, without further ado, I will stop sharing so you can take control and
okay.
Take it away.
Yeah, thank you, Mike. It was a wonderful introduction. Get used to it. So let me share my screen and we'll start with the slides. It should be there. Just give me a little feedback.
Yep, I can see it. Perfect.
Okay, so let's go ahead. So in this webinar, we'll talk about glare and photobiological safety. So this is two topics, actually, glare and photobiological safety, that are addressed in the latest report that was issued by the Solid-State Lighting and Controls Platform. And it was published just last month. And so I'm one of the authors, together with researchers from Canada and Australia. This report is publicly available, so you can download it on the website, and you also have an access to the recordings of the webinar as well, as Mike said before. So the first question we can ask is, why review, again, the effects of LEDs and solid-state lighting on health? Well, we still have users complaining, that's a fact. Second point, the individual exposure to LEDs has globally increased worldwide, and not necessarily because of lighting, but because of displays and toys and gadgets. Everything around us now contains LEDs. We have new knowledge about how light interacts with our health, so advances in physiology and medicine. Also, a new focus on inclusiveness. Lighting should be adapted to everyone, including sensitive people whose existence should be recognized and specific needs too, derived from their sensitivity. For lighting manufacturers, our work can help identify which features of LED lamps and luminaires can be improved to achieve better outcomes in terms of health and well-being. So we would like to provide guidance to the lighting industry And it's a good thing, I think, to reduce the negative health effects because it goes along with the improvement of quality of light and customer satisfaction, which is very important. We would also want to improve public health and raise the awareness of the public, especially for sensitive people who need to be aware of the adverse effects of light, and also inform people of the importance of a proper exposure to light and to darkness, actually, in everyday life. So this is not the responsibility of lighting manufacturers to do that. It's our own responsibility as users of light. We would like to improve lighting regulations, standards, procurement specifications, and of course, as researchers, we would like to identify areas where more research is needed. The scope of this report and this webinar is general lighting, concerning lamps and luminaires for general indoor and outdoor lighting. So products out of scope are everything concerned with automotive lights, toys, displays, although they contain LEDs and although some conclusions might apply to them, but they are not in the scope of our search and review and work in general. So this work is an international collaboration directly funded by governments. So France, in this case, for me, Canada, with the NRC, Jennifer Veitch, and Australian partners, a public institute, the ARPANSA, it's the Australian Radiation Protection and Nuclear Safety Agency. And we worked with money from governments and also from the SSL platform itself, funded by governments. The method, we based our work on reviews of reviews, actually. We reviewed what was reviewed during the past decade. And when reviews weren't available, we had to identify individual research papers through literature search during the last decade. And we also examined standards, guidelines, collective appraisal reports from health agencies, and many technical reports that were available. So let's start by glare, the first part of this webinar, about 30 minutes. Glare is the fastest adverse effect to be experienced with lighting. It's a physiological phenomenon. It's not in your head, as some people say. You can often hear people say that glare is psychological, but no, it's actually physiological. The number one complaint about lighting, actually, it's very commonly and very easily expressed by users. We can easily put a name on what we feel when we face a glaring source. It's glare. We have some immediate consequences on visual performance and indirectly some consequences on accidents and falls. It's easy to fall when you have a glaring source in your field of view. You also have health consequences, more subtle consequences, more difficult to measure after prolonged exposure. And there are very sensitive populations to glare. Everything is not equal. So we have different forms of glare that are very well described in this good book from Peter Boyce about human factors in lighting. So I will just explain those different forms of glare briefly. The most violent form of glare is saturation glare. When you have too much light, the light levels exceed the upper limit for vision. You have saturation in your field of view associated with a sensation of pain. It might be hazardous, especially with the sun, where you can have burns on your cornea and thermal injuries on your retina. So it really touches the field of photobiological safety. Adaptation glare is a transient phenomenon due to a rapid increase of light level, and vision usually takes a few seconds to adapt. You can experience this when you drive out of a tunnel, for example, and you start seeing outside the outdoors. It takes a while to adapt and you are temporarily glared. Disability glare. It's an interesting phenomenon because it's caused by light diffusion within the eye. And this diffusion, intraocular diffusion, forms a halo around the bright lights, and it's seen when you have dark backgrounds. Otherwise, you don't see that. So you see it at night, essentially, with bright outdoor lights. So it reduces the visibility of dimmer objects because of this sort of veil in front of your field of view. And it's strongly influenced by age. The more you age, the more diffusion you have in your eye. So it's mostly experienced at night. It can be experienced completely without discomfort. That's the most interesting part of this disability glare. It's not painful at all. It can be painful if it's associated with a high contrast or too high a level. But the fundamental form of this halo surrounding bright light is that it's completely painless. We currently have no research papers investigating disability glare from LEDs compared with older technologies. And we have some anecdotal reports showing that there shouldn't be any difference. So those photos illustrate some examples of disability glare. You see a perfectly circular halo. So this on the left side is a photo taken by a sensor, not by your eyes. So it's not perfectly circular, and you have stripes here that are not visible with your eyes. But when you look at a stadium light, in this case, you can see this perfectly nice halo resulting from light scattering in your eye. It can happen with the sun also, and the veiling phenomenon resulting from this diffusion of light in the eye varies between young subjects seeing something and older subjects seeing nothing, basically, two extreme cases. Discomfort glare. So discomfort glare is not a very good term. It's mainly due to luminance contrasts in the field of view. It's very common with indoor lighting, but still very difficult to assess. It's one of the top-rated factors in indoor environmental quality. When you have glare, it comes number one because it has no inertia. You experience it straight away. We have a large body of research work since more than a century, and we have new concerns with LEDs and solid-state lighting in general. So in those photos here, you can see a nice example on the left side of a luminance contrast between a black painted ceiling and very small, dark painted or black painted ceiling. Yeah, that's what I said. And bright sources, so an extreme contrast in terms of luminance. And on the right side, it's more an industrial setting or a school, something like this, difficult to tell. But you still have a high luminance contrast between the visual field, the view, and those luminaires, very bright. So discomfort glare is associated with a high luminance contrast. Luminance is measured in candela per square meters, and it doesn't necessarily need some high luminance at the eye. So the lux that you can measure at the eye with the lux meter can be very small. It has nothing to do with the luminance contrast. So the root of discomfort glare is the difficulty for the visual system to maintain a high dynamic range in the field of view for a long time. So as a consequence of this difficulty, you experience discomfort, annoyance, stress, aversion response. But the main thing is that you can still, although it is difficult, maintain visual performance. You have no halo around light sources, like with disability glare outdoors, but you have to make efforts, and this has consequences. It's tiring. Just a remark at the bottom of this slide, the term discomfort glare is somewhat misleading, suggesting, as I said before, a purely psychological phenomenon. It's all in your head, but it's not in your head. And it would be better, I think, to call it contrast glare instead of discomfort glare, because discomfort is something that you experience as a consequence of luminance contrast. It's actually discomfort from glare. And discomfort is something that is subjective, that can be assessed by psychophysics or psychological methods. Discomfort glare, as I've just said, is assessed using psychophysics, individual judgments based on stimuli controlled, usually in a lab, not always, sometimes based on questionnaires using psychometric scales, with protocols not always free of bias. So discomfort glare is physiological. Therefore, we have a new set of new methods that have recently emerged to monitor physiological and behavioral response to glare, including eye tracking, EEG, fMRI, functional magnetic resonance imaging, brain oximetry, measuring the oxidation, the oxygen in the brain, so reflecting the activity of the brain. So here are a few references about such work. There are more in the report. And here a picture of a colleague of mine of ENTPE in Lyon, Dominique Dumortier, for those of you who know him. And Dominique is wearing on this picture many different kind of sensors, physiological sensors. And it's an extract from a PhD thesis from a colleague in France, Mathieu Yodis. So this is really a change in the methods traditionally used to assess glare. So what was learned from physiological responses? This body of work have provided direct proofs that reading performance is decreased under a glaring source, and that was measured using eye tracking. Very good at assessing visual tasks, reading tasks especially. Glare influences many other parameters when you use eye tracking. Saccade speed, fixation time, blink rate, pupil size, and those are not consciously perceived. So that's interesting, but we still need a lot of more research to identify the most significant parameters, what correlates best with the subjective impression of discomfort from glare. So it really depends on the task. So when you have different teams of researchers investigating several types of tasks, you don't get the same markers, and it's very difficult to know what is more significant, I would say. But anyway, it's still very promising. When we want to know what happens in your brain when you are faced with discomfort glare, it's a new body of work looking at neural correlates. So those researchers found a link between visual discomfort and the increased blood flow in the brain. So the hemodynamic response in technical terms, especially periodic patterns are very critical. When you have a black and white stripes, such as this, you have a very marked annoyance phenomenon, very similar to flicker, actually, where you have sort of resonant frequency at the temporal frequency in the case of flicker, and the same thing happened with spatial frequencies. Some of them are very uncomfortable to look at. And a few examples here. It's not uncommon, unfortunately, in lighting to have those very strongly marked patterns of white and black luminance. So here are a few examples that can make people feel a little dizzy or uncomfortable with viewing that. And the same thing happens with the non-uniformity of luminance in the light source. We found in the literature that the non-uniformity increases discomfort. So it's quite well understood. There were a lot of research papers, and they were all examined within the CIE, and it led to a new UGR index, especially modified to account for the non-uniformity of the light source. In outdoor lighting, we also have a non-uniform luminaires, such as the one here on the right side, but we have no study investigating the discomfort and glare from those types of luminaire outdoors seen by pedestrians, for example, at close range, short distances. Found in reviewing the literature that there is an influence of spectrum and color on discomfort glare. So consistently, we have different teams reporting that cold white LEDs are more glary than warm white LEDs with the same luminance and the same conditions of vision. But we have several models of spectral sensitivity. So it's good because they more or less look the same, although there are some disagreement in the blue region here of the spectrum. And there's a disagreement because discomfort glare varies a lot between central vision and peripheral vision. And of course, short wavelength cones are more important apart from the central vision in moving to the periphery. And in some models, you see an importance of the sensitivity of the short wavelength cones in the discomfort glare. So you have here two references. So there's still no agreement. We have no standard, but we should move to elaborate a consensus on such a curve and introduce a spectral correction in the UGR, for instance. Effects of age on glare. So we found that children and young adults experience more discomfort from glare, and they experience this faster compared with older adults. They tend not to complain as much, but when you measure the thresholds of luminance, for example, in young subjects here on the white bar and older subjects on the gray bar, we have lower luminance thresholds, meaning that they are more sensitive to glare than adults. It happens a lot for the blue light, green light, amber light, but not so much for red and white light in this particular study. Another study showed that when you have a long exposure to discomfort glare, the visual performance of subjects over 50, so older adults, decrease in low light conditions, but after the exposure. So you have a sort of delayed effect of long exposure to a glare source. There was also some work about circadian aspects of discomfort glare. Although there are a limited number of studies, those studies found that discomfort from glare increases during the day. So we have a greater sensitivity to glare in the morning, which is surprising because we are often told by circadian people that we need a lot of light exposure in the morning. But we must be careful because we are more sensitive to glare in the morning. So we need more light, but not maybe focused and with lower levels of luminance. The discomfort experience from glare is influenced by the chronotype. So people with early chronotypes, the early birds, are not as sensitive to glare. Mechanisms behind that is not known, but there are current investigations on the role of the RGCs, the cells involved in the circadian regulation of the biological clock. Now, moving to the health effects of glare. Glare was shown to trigger and aggravate headaches in people suffering from migraines. And surprisingly, the green light, when you when people studied the influence of colors, monochromatic lights almost, the green light was found to be the least active in triggering headaches. An extreme form of discomfort is called photophobia. This is the fear of light. And we have a lot of sensitive people and a lot of people who experience this fear of light, actually. And some researchers found non-visual pathways through various nerves, not only the optical nerve, but the trigeminal nerve. And they found that there was a possible action of light on pain processing mechanisms, pain receptors, if you want. We found that prolonged exposure to glare contributes to asthenopic syndromes, such as eye fatigue, eye strain, and also muscular pains in the neck, for instance. And of course, as I said at the beginning, when you have a glaring source in your field of view, your vision might be impaired and you are subject to accidents, falls, and various occupational hazards if you work with tools and machines. We have the UGR metric to quantify indoor lighting, discomfort glare from indoor lighting with various variants, the small source UGR. We have a CIE technical report to generate tables of UGR that are used by lighting manufacturers. And we now have, since 2019, a UGR for non-uniform sources, as I mentioned before. In outdoor lighting, we have several models that are well established to describe glare, Adrian's model and other more recent models. My French colleagues still carry a lot of work to better know discomfort glare outside, especially for pedestrians. So glare coming from a moving source or combined sources, several sources of glare in the field of view. Very interesting research. And you can find a CIE technical report summarizing the knowledge about discomfort glare in road lighting and vehicle lighting. So the metrics for outdoor lighting glare mainly apply to disability glare, such as the GR index, which is used to design stadium luminaires, or stadium lighting, I would say. The threshold increment, TI index, describing disability glare of vehicle drivers by road lighting. And of course, it's very tricky to use the UGR indices outside. They are not validated outdoors. The effect of non-uniformity of luminaires outdoors has not been sufficiently studied. I said that. And the effects of multiple sources in the field of view are currently being investigated. So main conclusions on glare. Glare is still the #1 source of complaints, so we should never forget that. It alters vision during and sometimes after exposure. It's known to trigger headaches and eye strain, especially with sensitive people. There's an importance of designing the products very well, so good optical design, because the size of the luminous source, its luminance, its non-uniformity are all important parameters at the product level. We have an influence of the spectral distribution, but we still don't understand everything happening in the brain. So the neural mechanism starts to be studied. We have results, but we don't know everything yet. The influence of age has been demonstrated as well. So some recommendations in indoor lighting. We have good feedbacks in the literature from large area uniform solid-state lighting luminaires. Of course, if you have non-uniform luminaires, please use the UGR correction that was provided by the CIE to assess discomfort glare. The optical design of SSL products should be improved, especially the need to hide the LEDs, the individual LEDs from the direct view. This is very important. It's not always possible, so sometimes we need to use diffusers. And if it's still not possible, for example, when you buy just an LED filament lamp, for example, you need to use a shading device and not direct the source towards the eye. So guidance should be also provided to the general public and to the lighting designers. There are sensitive people to glare, migraineurs, children, and young adults. And there's a link with temporal light modulation because we found the same categories of sensitive people with temporal light modulation. Night workers, they are more sensitive to glare because of the circadian sensitivity, but they are also more exposed because when you don't have daylight in your environment, the luminous contrasts are always higher than during the day. Drivers and pedestrians at night, they are always exposed with the automotive lights, with the road and street lighting. And workers using strong lights, so lighting professionals, this is us. We always work with light sources in our labs, in our assessment and measurements and expertise. But athletes are also exposed if they are on big stadiums. And stage artists, they are always illuminated with very powerful light, and it's very often glary for them. Some recommendation for migraineurs: they should avoid direct viewing of high luminance solid state lighting sources. They should reduce luminance and luminance contrast in the field of view, avoid periodic patterns, and cold white light should be used with care if possible and if necessary. Older adults should avoid long exposure to glare because of possible delayed effects on vision, and people working at night are more exposed. Knowledge gaps. So we don't still know about the effect of non-uniformity in darker environments outdoors, the combined effect of multiple glare sources. We still don't agree about the spectral sensitivity to glare. That should be very useful to know. The role of the photoreceptors taken individually is not very well known, including the ganglion cells. There's an influence of the circadian clock that should be further studied, as well as the neural mechanisms, the influence of age, what happens with children. There's not a lot of studies with children. It's none, actually. All the studies were made with young adults and older adults, I would say. No children so far. And we don't know the dose-effect relationship between glare and headaches, glare and eye strain. So we know that after 8 hours, we do get some headaches. Many sensitive people do, but we don't know the dose-effect relationship. And of course, it's very difficult for lighting people to carry out provocation studies. We need a medical study for that, and we need to work with doctors and clinical environment, maybe. Okay, so we have another 30 minutes, maybe a little less, to talk about photobiological safety now. Photobiological safety includes all the acute effects of optical radiation on the eye and on the skin. So actually, everything should be photobiological. The influence of light on the biology, vision is photobiological, glare is photobiological, but in its normative acceptance, photobiological safety is really the acute effects on skin and eye, typically a burn, things like this. So when you have optical radiation, whether it is UV, visible, infrared, you can have thermal effects and photochemical effects on your skin and on your eye. In general, visible light from LEDs is harmless for the skin unless you have lupus or rare conditions, or if you take photosensitive medications, certain antibiotics, but it's very rare. It's definitely not in our scope. UV and infrared may cause injuries to the eye, but the cornea, the iris, and the lens. And now the good thing with LEDs and our solid state lighting products is that we have no infrared and no UV. So it's a straight reduction in these risks. So what remains are retinal hazards. So image forming effect, I would say, because everything falling on the retina passes through the lens and is image related. Retinal hazards happen with visible light, near infrared, which is also focused on the retina, and near UV, especially for sensitive people who don't filter UV, for example, people without the crystalline lens or young children. So the retina is made of a whole complex setup of layers. So what we need to know for now is that we have photoreceptors here, cones and rods, and we have this layer of cells on which the cones and rods are connected, and it's called the retinal pigment epithelium. It's a very important layer because it forms the barrier between the blood circulation and the outer retina and the photoreceptors. And this layer helps the photoreceptors to regenerate after they are exposed to light. There's a whole cycle implying the retinal pigment epithelium, RPE. So retinal hazards, what can happen to your retina with light? You can have burns on your retina, but it mainly happens with near infrared. So it's called the retinal thermal hazard. And it was never demonstrated with LEDs used in lighting systems. You can maybe have this with infrared LEDs. And you have two types of photochemical hazard, retinal photochemical hazard. The type 1 is very rare. It's something that is associated with high intensity saturation glare. The level of light is so high, so whatever the wavelengths, you have your photoreceptors dying and your retina is all whitening. So the spectral sensitivity is flat, and it very rarely occurs in our everyday life, and not with LEDs. So what remains and what is relevant to LEDs is the type 2 photochemical hazard, and it's called the blue light hazard, BLH. Photochemical reactions in this type of hazard are triggered by short wavelength photons, blue, violet, and UV, and they really destroy or interact with the RPE. So it makes the cells of the RPE die, and in turn, if the RPE is injured, the photoreceptors will die too. And this risk is very dependent on the wavelengths. It's a photochemical hazard peaking at around 430 to 440 nanometers. So it's blue, not violet, but blue. Glare may or may not happen with the blue light hazard. Glare is not necessarily the first signal of a photobiological hazard. If you look at a blue LED, it might be very powerful with a lot of radiant intensity, but a very low luminous intensity. So the visual stimulus associated with a blue LED can be very low. So you don't get this aversion response that is very strong with bright white light, with monochromatic blue or single color blue. So we have to watch out the blue light. On the left side of this slide, we have an extract from a case report of an injury happening with an accidental exposure to a 5-watt LED torchlight. And the doctors who wrote the report found that the injuries on the retina were very similar with injuries coming from solar eclipses. It's a spot very similar to a solar maculopathy. So what happens when you look at the sun directly during a solar eclipse or not. Or you can also observe that on patients doing welding without the proper eye protection. And on the right side, it's two photos of a retinal pigment epithelium of a rat. So rat retina, non-illuminated. When it's non-illuminated, you see the cells are perfectly tight all together, and nothing can really go through the membranes because it's completely proof, tight proof. And after 6-hour exposure to blue light in this specific study, it's very interesting to see that the cells are not jointly connected together, and they let something go in between. So the RPE is not properly functioning, and if you wait for longer exposure, you can have cell death and a lot of consequences in photoreceptors in turn. So the risk associated with this blue light, the blue light hazard, I shouldn't say risk, because risk is also a result of exposure and the probability of this to happen. So the blue light hazard is described by a sensitivity function, a spectral sensitivity function. It's called the B lambda function, peaking in the blue, but extending to the red, but at very low level. It's a logarithmic scale here. So when you look at the spectral distribution of a white LED here, it has a blue peak, and strangely, the, the blue peak is in the region of B lambda. So we can say, how bad is the blue peak? And it's actually a very bad question to ask. We have really to be careful about this type of interpretation because it's purely graphical, and most times it's a wrong interpretation. So looking at this graph, I can't say that this white LED is associated with blue light hazard. It's not possible at all. Why is that? Because we use a single graphical interpretation of the spectral distribution of light. So this one on the left, the most common is the spectral radiant flux. So radiant quantities, radiometric system. And we have a blue peak here and a phosphor peak. But if we move to another graphical representation in the photon system of units, so counting photons instead of counting watts, and if we chose an x-axis plotted with frequency, which is proportional to the photon energy, we found that the blue peak is not the peak, actually. The peak is in the yellow-orange range here. And the blue peak is just a secondary emission. So what is true, what is not true? Both representations are perfectly valid. And that is emphasized in this publication that you can access freely on lighting research and technology. And it gives a lot of examples like this associated with misrepresentations of action spectrum, such as the B lambda function and spectral distributions. So we have two different representations. And what is interesting to see is that the shape of the spectral distribution changes between representations, and even the location of the peaks change. For example, here, the phosphor peak is at 565 nanometers, but on the frequency representation in the photon system of units, the peak is at 591 nanometers, so almost 40 nanometers away from this representation. But it's actually, both are actually true. So what is better suited to the assessment of the potentially hazardous spectral distribution in relative value is the blue light hazard efficacy of luminous radiation. It was defined by the CIE in 2014, and it quantifies the amount of energy that you have in comparison with the photopic output expressed in lumen. So the quantity is watt per lumen. So in this graph, the blue light hazard efficacy is plotted with the correlated color temperature. So there's a sort of linear correlation between blue light hazard efficacy and CCT, but it's not perfect. If you look at warm white LEDs here, you can have a factor of 2 for the same correlated color temperature. And the efficacy can vary quite a lot for the blue light hazard. So it's not possible to do an assessment of the blue light hazard using this type of representation. It's not enough. If you look at the behavior of B lambda in comparison with the sensitivity of the photoreceptors, you find that B lambda is really something else. It sort of aligns towards the long wavelengths with the sensitivity of the S cones, the short wavelength cones. But on the right side, there's nothing visual here. It's just the action of photons on the RPE and not on photoreceptors. So this is not explained by vision. People who have a greater transparency of the eye should be described in terms of retinal sensitivity with the A lambda function instead of the B lambda function. Because the B lambda function drops off towards the UV because of the filtering of the crystalline lens and the cornea, but mostly the crystalline lens. And people having a very transparent crystalline lens, such as very small children, or sensitive population, people without crystalline lens, or pseudophakic, it's people wearing lens implants. So after a cataract, they remove the old crystalline lens and put an implant instead. And they should be assessed with this curve. This curve goes all the way to the UV, actually. There's no short wavelength filtering with those sensitive people. We have normative limits for the blue light hazard, and it's really related to what happens in terms of retinal irradiance. So we must keep in mind that the blue light hazard is an image forming effect. So when you have a light source, the eye forms an image, and this image is associated with a illuminance on the retina, and this is this illuminance on the retina that is associated with the risk. So the damage threshold on the retina is expressed in terms of retinal irradiance dose in joule per square centimeters. It was found to be between 20 and 30 joule per square centimeters. And those results were found by Ham and his colleagues in the 70s, actually, one single team about almost 50 years ago. And the ICNIRP, the body in charge of setting limits for optical radiations, set a limit value of 2.2 just by applying a safety factor of around 10. But they transposed this retinal dose to the luminance dose of a source, because it's not really convenient to do lighting design using an illuminance dose in the retina. So we need to transpose this exposure limit on the retina into a source emission limit, which in this case is the radiance dose of blue light emitted by a source. So the exposure limits of the ICNIRP is actually an emission limit of 10 to the 6 joule per square meter per steradians. It's a dose of radiance. Now, moving to the research, what we found during this review was that the blue light hazard was detected by several teams below this current exposure dose limit that I told you about in the last slides. And two reasons for that. The detection methods greatly improved. Now we have very sensitive techniques that can detect retinal damage before being visible with the old techniques that were used in the 70s. And we have studies on other animals, many rodents and also monkeys, macaques, and they showed retinal, some researchers showed retinal damage with exposures below the current limit. And I give you here a few references. So the first reference is a paper that was just published 2 or 3 weeks ago, and that was not included in our review. But a previous study of this team was published in 2012 and already showing some sub-thresholds effects of blue light. We found that the retina of children is more exposed just because of the characteristics of the eye. The biometry, the dimension of the eyes are not the same. And also the crystalline lens is more transparent. And when you combine the size effect and the transparency of the crystalline lens, you find that for the same level of light at the eye, children can receive up to 3 times more light on their retina compared to adults. Also, we found that the aversion response in children is not fully developed, and it can be bypassed on purpose. So children can really stare into a light source without being bothered as much as adults. The retina is more sensitive at night. We found some work from researchers studying on diurnal animals, the circadian variation of phototoxicity. And actually, retinal phototoxicity increases at night when the retina is supposed to rest and clean itself through a process called phagocytosis. The literature revealed some protective effects of longer wavelengths, red and infrared. So this is a new area of research. Photobiomodulation is the new terminology for using red and infrared light to heal in clinical environments, mostly to heal the skin and the eye. And we found positive effects on the retina, an accelerating healing process through the better phagocytosis and better enhanced mitochondrial activity of the RPE cells. So it's promising in medical applications to cure several or various retinal diseases. But in general lighting, we don't have enough results to demonstrate that enriching the spectrum with red and near-infrared light could attenuate the blue light hazard, for instance. It's too early. If we look at standards, so the common standard to assess the hazard of light sources, the photobiological safety, is the IEC 62471, which is the same as CIE S009, and this standard is based on the ICNIRP emission value. So this ICNIRP emission value is valid for adults without eye pathology. It's not applicable to children, and it's not applicable to sensitive people having various conditions. So this standard uses a measurement protocol, and based on the luminance emitted in the blue region of the B lambda curve, we get a certain exposure time needed to reach the exposure limit. And according to this exposure time, we can classify the lamp or the luminaire in several risk groups, from risk group 0, no risk, up to risk group 3, high risk. So we examined the published product emission data during this last decade, and we found, that is good news, that SSL products sold in the last 5 years for domestic and office lighting are comparable with halogen and fluorescent lamps in terms of the blue light hazard. So they were all found in risk group 0, no risk, or risk group 1, low risk, as were the old legacy technologies. However, when we look at results that were measured, that were coming from measurements on bare LEDs, I would say components, cold white LEDs, blue or near UV, if you look at them directly, you can reach the maximum exposure time, so exceed the exposure of your retina in times as short as 15 seconds. So most of these LEDs are classified in risk group 2, and the LED manufacturers know that and clearly specify the risk group being 2 for those LEDs. We don't have data that were published about high power professional LED luminaires. So we don't really know the levels of those big stadium luminaires or stage lights, which is a problem. So here a reference of published data, some list of papers where you can find data. And here is an extract from one of the papers published quite recently, 5 years ago, by an American team, Below, Bierman, and Mark Rear. And it's interesting because there's a comparison of the level of blue lights from the blue sky, then from LEDs, then from the sun. And it's a very common remark that I often get is that if the blue light hazard really exists, we shouldn't be able to live under the blue sky. Well, it's a wrong remark, it's a wrong assumption, because blue light is associated with a high luminance, for example, 10,000 lux at the cornea, but a very small luminance and blue light radiance. It's a diffuse source, and you have to remember that blue light hazard is an image-forming effect. On the opposite, if you take a white LED, it has a low illuminance at your eye, but a high luminance. So here, 100 lux at the eye, but a luminance of about 1 million candela per square meter. So this explains the concerns about blue light hazard from very bright sources. Of course, the sun has both a high luminance at the cornea and a high luminance, so don't stare at the sun. So the main conclusions on the photobiological safety: the blue light hazard remains a concern, and it is still under investigation by several teams. They found a consistent detection of retinal damage below the current exposure limit. It was found that retinal phototoxicity increases at night, and children are not sufficiently protected by the current standards and regulations. Protective effects of near-infrared light and red light on the retina were found. The sensitive people to the blue light hazard are children, people with retinal diseases, people wearing lens implants, and night workers. And highly exposed people are workers using strong lights, same as the glare category, really, all those lighting professionals that we are. Athletes, artists exposed to big, powerful SSL luminaires. So recommendations: we recommend to update the blue light hazard exposure limit. We recommend to update the safety standards by considering sensitive people, including children. We should not apply more permissive standards before these updates. We should strengthen photobiological safety requirements for people exposed at night and people with a reduced aversion response to bright light. There's still some knowledge gaps. We could form research priorities. We should gather emission data on high-power professional LED luminaires and also on new white LED technologies, especially LEDs using a UV pump, because they might leak a little UV light. We don't know, we don't have data. Effects of simultaneous exposure to blue and red light. It's worth investigating because we might benefit of a spectrum enrichment in preventing retinal damage, but we don't know. So this is something that researchers should investigate, and the influence of age and age-related pathologies on the sensitivity to short wavelength light. Finally, we can emit some policy recommendations for both glare and photobiological safety. So manufacturers should design products with the least possibility of glare and retinal hazard. Standardization bodies should include expertise on health effects, developing limit values for validated quantities, and ensure that sensitive populations get due consideration in safety standards, which is not currently the case with photobiological safety standards. Regulators should include photobiological safety and glare among the specifications required for SSL products. And they should reference appropriate standards and use validated quantity to establish limits for glare and photobiological safety in regulations. And finally, people involved in energy efficiency, energy savings, people involved with regulating equipment should engage with public health authorities to ensure that public spaces do not expose sensitive individuals to glare and retinal hazards from SSL. These recommendations can be summarized in 2 sentences, basically. Products should be designed in an intrinsically safe manner, and they should be installed very carefully. So the lighting practices should be more careful with respect to glare and photobiological safety. And the last word before ending, just to remember that light is made of photons, and photons are elementary particles. They are all the same, whether they come from a fluorescent lamp or an LED. So they all carry their own energy and momentum, and they are all scattered and absorbed and re-emitted by matter and tissues. But these effects are technology agnostic. They don't depend. The photon doesn't know where it comes from. So with that final remark, thank you for your attention. And I can stop sharing to open the Q&A part of this webinar.
Super. Thank you. Thank you, Christophe. That was excellent. Yeah, so we are now in the Q&A part, as Christophe mentioned. So if you have some questions, you can click on the Q&A button at the bottom of the toolbar there and type your question in, or raise your hand and I will unmute you to ask your question. And we do have a hand raised already, so I will unmute you now, Christian, and see if you can unmute yourself and ask your question live. Let's see if that works. So, Christian, are you able to? Good. Go ahead. We can't hear you. Can't hear you yet. I can see you've got a microphone, but yeah, sorry, Christian, we're not hearing you.
No, unfortunately, maybe Christian can type his question.
Maybe type the question, and we'll take this first question here from Anne Bay. So Anne asks, Christophe, are there any plans of making the BLH standards easier to work with for measurement people?
Not really. It's still a tricky assessment. It requires some skills and has to be done by really specialized labs, accredited labs, I would say, because it's a matter of safety. And it's not easy to have an easy assessment. Maybe pre-assessment can be made by lighting designers or lighting practitioners according to correlated color temperature and brightness. But still, the full assessment requires very specific measurements, especially if you also investigate the UV part and the infrared part, if you have a complex luminaire having LEDs not only emitted in the visible range. And it's really technically complex, I would say. So I don't know. I don't think there are plans to simplify this because it's basically complicated.
Okay, thanks. Next question is from Tapio. So Tapio asks, at lighting fairs, many lighting manufacturers present very low UGR values for fixtures with non-uniform luminance on the light aperture. Do you think that those UGR values are calculated using the method described in CIE 232, discomfort caused by glare from luminaires with a non-uniform source luminance?
I don't know. I don't know if this is well known, if this CIE recommendation or CIE non-uniformity correction is very, very well known by the community. Maybe lighting manufacturers use it, but everything that I've seen so far was generated using the tabulated method for UGR, so not including the non-uniformity correction factor. So I would be tempted to say that no, lighting manufacturers don't use this UGR, this non-uniformity correction, but it's not possible to be affirmative at 100%.
Thanks, Tapio. Oh, and a follow-on question from Tapio. Is the CIE 232 system use lighting calculation programs, for example, in Dialux? If not, when will it be?
Oh, I don't know. We have to ask the Dialux people. I know that it's not the non-uniformity corrections need a sort of near field measurement. We need a luminance image of the light source in several directions. So either you can use a near field photogoniometer or an imaging luminance meter device, basically a camera calibrated in luminance. And if it's properly calibrated, the CIE 232 gives you the procedure to work out the non-uniformity correction index from this luminance image. And it's quite complex also, so it could be integrated in lighting software. Yes,
And
of
just a
course. Yeah.
so, yeah, I was going to read Anne Bay, who's with Viso Systems in Denmark. Anne writes to Tapio, in our experience, not a lot of people love CIE 232 because values get higher. So that's
It's also the reality. Non-uniform luminance not perform as well as glare, as far as glare is concerned. So it's the reality, not always flattering.
mhm. And I think Anne's just put a follow-on comment. So before I go to John's question, I'll just read Anne's comment. It's quite right that luminance images are needed. However, it is very complex to know the relevant direction.
Mm. It's
Okay.
true.
Yeah. Yeah. Thank you, Anne, for that. Okay. John McHugh asks, with LED street lighting based on a high luminance area source versus the legacy sources being a point source, does this change the evaluation of street lighting glare? Does the impact of the BUG rating, does this impact the BUG rating of
Mm.
street lighting?
So I'm not familiar with the bug rating. It's used in the US or in North America, and I'm from France. So I know of the BUG bug rating, but I don't know how it performs with non-uniformity. According to what I know, but that would need verification, it still relies on far field intensity distribution data. So a point source, even if it's not a point source, but it's the IES file that is used to determine this bug rating. So it's not really accurate when you have an extended light source outdoors. And it really makes a difference for glare. I mean, perceived glare uh, is really dependent on the size of source. And in these outdoor lighting evaluations, all the standard methods rely on equivalent point source using the far field luminous intensity distribution. So there's room for improvement there. So both for the finite size, the extended size, and the non-uniformity.
Great. And I've just unmuted Anne if she'd like to. Thank you for that answer. Anne's added it. It does not influence bug rating, which is just lumens in certain direction ranges.
Okay.
Anne, would you like to elaborate on your answer there
Yes, I
for
think you
John?
can hear me now, right?
Yes, we can. Yeah.
Okay. So you can say bug rating is a great system just to evaluate the directions of light, and but it's more concerned with, you could say, the amount of lumens in certain directions, whether it has a throw over the street or the pathway next to the street. So it's not really related to luminance as such. So it doesn't, whatever you do with luminance distributions, it doesn't impact bug ratings. So that's more or less it.
Okay. Great. Thank you, Anne. Okay. Next question here from Jean-Michel. He asks, the new standard IEC 62471-7 2023 now applies to the luminaire safety standard IEC 60598-1 version 10 of 2024. IEC 62471-7 no longer uses risk group classification, but imposes a limit brackets in blue light radiance close bracket, depending on the application and an assessment distance. I note that for most applications, the limit exceeds the old RG1 limit. For example, ceiling lighting equipment assessed at 1 meter in place of 200 millimeters have a blue light limit of 100,000 units, as watt meters per 2 steradians in the denominator, in place of 10,000, corresponding to the R1 over RG1 over RG2 limit. So much less strict. This is not in line with your recommendation. Are you analyzing this new standard as I am?
Yes, thank you for this very good question.
Can you speak a
We
little louder, Christoph? Sorry, the
Okay,
microphone's
yeah,
a bit
thank
soft.
you.
Yep, thanks.
It's a relevant question actually, and we did analyze this new standard in our report because it's a typical standard that is issued without any new medical or physiological research. There was no review behind this, and it was not assessed with the relevant set of expertise, I would say. Because at the end, you have a very practical standard for lighting manufacturers, but more permissive than the current regulation. So it's a standard that sets new limits that do not comply with the current regulation of lighting products. This is a problem with some IEC standards. And in fact, this standard allows to use products in general lighting that are classified in the risk group 2 of the photobiological standard .1, the basic standard. So this -7 standard is more permissive, and we do not recommend that it is used. And we detailed our arguments in the report. So I hope I was clear, but it's actually a concern from the authors of this report.
Okay, great. And maybe Jean-Michel, if you download a PDF copy, you can keyword search on that number to find the narrative in the report on that standard. Thank you. Are there any other questions from the audience or anyone else who'd like to put their hand up and ask a question live? We're a little bit over time, but we could still continue if folks had other questions for Christophe. Okay, well maybe we will. Anne has asked a question. Any follow-up on CIE 232?
The non-uniformity, is it the one?
In terms of research.
Let me check. What is it the non-uniformity? Yes, it's the CIE 232 is the technical report about non-uniformity for in discomfort glare.
Yeah.
I don't know. I think there was a lot of research at the origin of this technical report, and we haven't found newer papers dealing with non-uniformity in indoor glare. So not that I'm aware of.
Okay. Okay, and you can unmute yourself, Anne, if you'd like. Saves writing lots of short questions. Go ahead.
Yes, I was just.
I would just mute one of you.
Just make a short comment on that. We say that the obstacle with CIE 232 is, of course, that almost none of the labs have luminance cameras that can actually be used for this. So it's, I think luminance cameras that can be used for this would start maybe at 20,000 euro or something like that. So it's almost out of reach for everyone. And also the obstacle is also that in practice, when you look at the luminance distributions from regular light sources, it's almost impossible to find out which direction is the most where you find the most severe luminance without checking it all. So you say that in CIE 232, I appreciate what they wanted to do was to find some representative directions to evaluate luminance in, and also representative of, for normal glare situations. But in our work, we found out that it's very often there's a surprise in there. You cannot actually guess where the most severe luminance is. So you cannot guess which direction to go. So we are also worried, you could say, that CIE 232 are missing out on some nasty glare as a cause of just checking two directions. So well, without putting a lot of words on it, I can say that we're working on something where we are checking many more directions and being able to provide luminance videos, if you wish, and having the system automatically find out where is the most severe direction.
Yeah, I think it's a very good suggestion, and it's based on practical difficulties that you experienced, and a lot of us experience that in laboratories. I'm sure the CIE is open to opening a new committee, a technical committee on this issue. Maybe there's already a committee. I have to check that,
Okay,
but it
don't
would
worry.
certainly be useful to improve this because, as you said, it's complex. Two directions. We are not sure to get the highest luminance level, and it's expensive.
Yeah,
That's true.
and we
The
actually face more or
luminance
less the
standard.
same challenge you could say when it comes to blue light hazard, because
Mhm.
well, you cannot also always guess in which direction actually to measure. So again, there's
Yeah.
some surprises in there. How do you actually detect that? And the standard doesn't tell you how to orient the luminaire
Yeah.
or the light
Yeah.
source when you're
Especially
checking
when you
it.
have optical systems.
Mm.
Mm. Yeah. Sorry, I interrupted you, but you're perfectly right. For when you have products with optics that are not symmetrical or they are not centered on the normal axis of the luminaire, and it's a typical case in street lighting, the intensity is larger at oblique angles, at large angles. It's difficult. It's difficult experimentally. You need to have a goniometer and you need to search for that maximum of light. It's not easy.
Okay. Good. Well, maybe on that research note, we can wind things up for today. Just say thank you again, Christoph, for the presentation, and thank you everyone on the participants for your joining us today. As noted earlier, I will be posting a copy of this video of this presentation as well as a PDF copy of Christoph's slides on the website tomorrow, and everyone who registered for the event will receive an email link to that tomorrow. So you can watch it again and yeah, enjoy it a second time. All right. Well, thanks everybody. Have a good afternoon, good evening, and good day. Bye for now.
Thank you. Bye-bye.
Bye-bye.